In the last lecture, we were talking about some of the technologies using which you can implement gates like diode transistor logic, transistor logic, and of course, CMOS. Now, in the present lecture, we shall be continuing our discussion on CMOS, and after that we shall be discussing about a few of the emerging technologies. Means emerging technologies are something which is slightly unconventional, but there is lot of opportunities for these technologies for developing future systems. So, I feel that it will be interesting for all of us to have some idea about some of these so called emerging technologies. So, the title of the present lecture is Emerging Technology, the first part. But before we move on to the just emerging technologies, we continue a little bit on CMOS. Now, here what we say, we are trying to develop some kind of complex switches. Okay. These complex switches, and these complex switches are called multiplexers. We shall be coming back to multiplexer in much more detail later. But what is a multiplexer like? Here we have a simple example. This is called a 2 to 1 multiplexer. 2 to 1 means there are two inputs A and B, there is one output Z. The way a multiplexer functions, that one of the inputs will be copied to the output. Now, which input? That depends on so called select line. Here S0 is a select line. If S0 is equal to 0, then the value of A will be copied to Z. But however, if S0 is 1, then the value of B will be copied to Z. So, you can say that this is like a multi-way switch. S0 is the control of the switch. So, either I connect A to Z or I connect B to Z. This is the basic idea. Now, this concept can be extended. For example, we can have a 4 to 1 multiplexer, where we have 4 inputs, let us say A, B, C and D, and we have an output Z. So, now this is like a 4-way switch. I am connecting one of these 4 inputs A, B, C and D to the output. Now, to select one of 4 things, I would clearly require 2 select lines, because in with one select line I had only combination 0 and 1, 2 possibilities. So, I have to select one of 2, but with 2 select lines I have 4 possibilities 0 0, 0 1, 1 0 and of course, 1 1. So, if S0 S1 is 0 0, then A is selected. If it is 0 1, S1 is 0, S0 is 1, then B is selected. If S1 is 1 and S0 is 0, then C is selected, and when both of them are 1, D is selected. So, there are many applications where these kind of multi-way switches find lot of interesting uses. Okay. So, first let us see how we can realize these so called multiplexer or multi-way switches using CMOS transistors. So, this is what we are trying to look at, how to build multiplexers using basic CMOS switches or CMOS transistors. Now, the idea behind is that from the various inputs, like for example, I can have inputs A, B, C and D, there will be multiple paths. The idea is like this, there will be multiple paths that will be connected to the output, let us say Z. Now, using some mechanism, we would be selecting exactly one of the path. Let us say we are selecting the second path, then B will be connected to Z, A, C, D will be disconnected. So, here among this parallel path we have to ensure that somehow exactly one of the paths get selected. Okay. And once you can do this, our multiplexer is implemented. Let us see how this is done. So, we require something called a transmission gate. Let us try to understand what a transmission gate is. You see, we have talked about NMOS transistors and PMOS transistors. This is an NMOS transistor, this is a PMOS transistor. Now, so when this switch is closed, say for an NMOS transistor, the switch is closed when you apply a 1 on the gate, this control input, and for a PMOS transistor it is closed when I apply a 0 on the gate. Now, some property of this transistor is that if you have an NMOS transistor and if we apply a low voltage here, like a voltage close to 0 volts, then in the output you get exactly 0 volts, no voltage degradation. But if you apply a higher voltage, let us say I apply 5 volts, then there is a drop across this transistor which is called the threshold voltage. So, in the output let us say we will be getting something like 4.2 volts, there will be a 0.8 volts drop. But for a PMOS transistor on the other hand, if I apply a 0 and the switch is closed, there will be a drop and the output will be 0. Let us say 8 or something. But if I apply a high voltage, this will be transmitted without any drop. So, you see the properties are complementary. So, an N type transistor can transmit low voltage very well, a P type transistor can transmit a high voltage very well. So, if I connect two such transistors in parallel, then I can connect or I can transmit both high voltage and low voltage equally well. This is the idea behind transmission gate. This is how a transmission gate looks like. Just like I have mentioned, you see there is a N type transistor, there is a P type transistor which are connected in parallel, and the gates of this transistor are selected together. Like I connect S here, I connect the NOT of S. S bar is actually NOT of S. Suppose I have a NOT gate, if the input is S, the output will be S prime. So, if S equal to 0, then both these transistors will be off. So, this switch is off. If S is 1, then both the N type and P type transistor will be on, and so X and F will be connected. Now, symbolically we represent it like this. This is the symbol of a so called transmission gate, where X is the input, F is the output and S is the select lines, S and S bar. So, you can see in one case there is no bubble, which means if S equal to 1, the N type is selected and the bubble is for the P type transistor. If S bar is 0, then this is selected, right. Now, using these transmission gates, you can very easily implement multiplexers. Let us look at this. A simple 2 to 1 multiplex. Well, here this is a connection. Fine. Now, you see how it works. There are two transmission gates I have used, one here and one here. At the inputs of the transmission gate on one side, I have the two input signals x1 and x2, and on the other side I have connected them together. This is my output f. Now, I have selected these two transmission gates using a select line S as follows. You see, S is connected directly here and this is also connected to the inverting input of here, and I have a NOT gate. So, on this side I have S bar, which is NOT of S. S bar I am connecting to the reverse side, to the non-inverting part of this and to the inverting part of this. So, what will happen if S is 0, you see, then which of the transmission gates will be on? S is 0 means this is 0. So, p type this will be conducting and yeah. So, this will be conducting and S is 0, S bar will be 1. So, this N type is also conducting, this transistor will be on. So, X1 will be connected to F, but if S equal to 1, the reverse will happen. S equal to 1 means a 1 will be connected here. So, this is off, this will be 0, this will be off, but on the other hand this 1 will come here and 0 will come here. So, this will be on. So, X2 will be connected. So, in this way I can have a 2 to 1 multiplexer very conveniently. So, using transmission gates it is very easy to do so. You can have a 4 to 1 multiplexer in the same way. I am not showing you the complete diagram, just giving you an idea. Suppose my 4 inputs are x 0, x 1, x 2 and x 3, and each of these lines I connect 2 such switches, 2 such transmission gates. I am showing it as a circle. Like this, and the outputs I connect together. Let us say I call it Z, this is the output. Now, there are 2 select lines, let us say S 1 and S 0. So, the way I connect them is that this switch is selected by S 0 bar, which means when S 0 is 0, this will be selected, and S 1 bar. So, when both are 0 0, this first path will be selected. Second row, this will be S 1 bar, this will be S 0. Third row, this will be S 1, this will be S 0 bar, and last row both S 1 and S 0. So, depending on the value of S 1 and S 0, you can easily see that exactly one of the path will be selected, that will be conducting both the transmission gate, and the corresponding input will be moving to the output, right. This is how multiplexers can be conveniently implemented using CMOS transmission gates. Now, later on we shall see some alternate ways of implementing multiplexers. We shall see that even using gates, the AND gate, OR gate, NOT gates, NAND, NOR we talked about, using gates also we can design and implement not only multiplexer, any kind of circuit or function that you want to. Okay. This we will see later. Now, let us talk about one kind of an emerging technology. Here we are talking about all optical implementation. So, what is the basic idea? You see, we are hearing that optical fibers are being used for communication. You must have heard there are a lot of optical fibers which have been laid under the ocean, connecting countries, connecting continents. They can communicate very fast, they have very fast communication speed and so on and so forth. Now, here we are saying that can we explore photonics or optics for carrying out some basic gate operation? Well, if it is so, then we can also implement some circuits using the manipulation of this kind of light or photons. Now, as a matter of convention, let us say that if there is a light, let us call it logic 1, and if there is no light, I call it logic 0. Suppose I have a torch in my hand, I send you a signal on off, on off, on off. So, you can read out the signal, on means 1, off means 0. This is one way of communicating. So, the idea behind optical communication is very similar. We send digital information using light, presence and or absence of light. So, let us see. Here we are saying that all computations are being carried out using light, and for that we require various kind of optical or photonic devices. So, I am not going into the detail, just very basic idea. There are some devices called interferometers, beam splitter when one optical beam is divided into 2 beams or more, optical coupler reverse, two optical beams are combined into a single optical beam, and as I said, as a matter of convention, presence of light will denote logic 1, while absence of light will denote logic 0. There are several approaches that have been explored. We shall be very briefly talking about one such technology, which is based on something called Mach-Zehnder interferometer. Let us see what a Mach-Zehnder interferometer look like and how we can implement some functions out of it. Well, here we have a very high level schematic diagram of a Mach-Zehnder interferometer. As you can see, it is a device which works on the basis of relative phase shift of two beams of light. As you can see in this diagram on the left, there are two paths which are shown. One is via here, other is via here. So, some optical beam which is coming, they get split into two parts and they follow two different paths, and in between these two different paths there can be some phase shift, and on the other side there is a coupler. This coupler, depending on the phase shift of the two signal, it will be either a constructive interference or a destructive interference. Constructive means the intensity of the light will increase, destructive means they will cancel out. So, depending on whether the phase shift is in phase or out of phase, on the output we shall get either a strong light or no light. If it is destructive interference, the two beams will be cancelling out and we shall not be getting any light in the output. Okay? This is the basic idea. So, on a plane, on the figure on the right hand side showed you the diagram, same diagram, that this is actually you can say your input where you are sending a beam. This is a some kind of a splitter where the beam is being split into two paths, one is flowing here, one is flowing here. Depending on the second input, this is also another input, depending on this the phase shift will be determined. And on the other side there is again some kind of a coupler which will be coupling the two signals in two different ways and will be generating two outputs, output 1 and output 2. Now, this kind of interferometer can be fabricated on silicon just like CMOS gates. Now, without going into the details of the optics, let us see functionally how this behaves. Functionally it behaves like this. I am showing a schematic diagram. This is my interferometer, this is my incoming signal and this is the control signal. Let us call them, okay, this is not A, this is B. Let us call them A and B. Okay. Here I have a coupler or a beam splitter and here I have another coupler, this is C2. And these are the two different paths. So, one beam will be following this path, one beam will be following this path, and depending on the control signal, the phase shift or the phase difference between these two beams will be determined. And the way Mach-Zehnder interferometer works is that in the two outputs which are traditionally called bar port and cross port, in terms of the logic, this implements AND, A and B, which means if there is a light on the input A and also a light on the input B, which means A equal to 1 and B equal to 1, only then this output will be 1, that means some light will come out, A and B. But on the cross port, it is A and B bar, that means if A is 1, that means there is light on A, but there is no light on B, then only this output will be 1. So, you can see these two outputs are generated. So, logically speaking, we can say that a Mach-Zehnder interferometer implements logic function, okay, let us call it B again, there is a typo, this is B, A and B. So, the outputs will be A B and A B bar. This is what Mach-Zehnder interferometer is. So, if I treat this as a black box, there are two inputs A and B, there are two outputs which are A and B, the other one is A and B bar. Now, let us see on the first output A and B are applied, we get A and B, that means we can implement the AND function. Let us also assume that I apply a constant 1 on the input A, that means there is a constant light here. Then what will be the output? The first one will be B and the second one, this A is 1. We shall talk about these operations in the next lecture. This will be B bar, because A is always 1, something and something is the other one, it will be B bar. So, we can also implement the NOT function, B NOT of B, and we shall see later that this AND and NOT, this set forms something called a functionally complete set, which means that if I can implement AND and NOT, I can implement any function I want. This implies that Mach-Zehnder interferometer can implement a functionally complete set and we can realize any circuit functionality. This is the basic idea behind Mach-Zehnder interferometer. This is one of the all optical technologies that I have talked about, where the input data as well as the outputs, they are represented as lights. If there is a light, I say it is logic 1, if there is no light, that is logic 0. So, this is a futuristic technology, because already optics or light is used for long distance communication using optical fibers. Even inside a VLSI chip, inside a circuit chip, there are high speed interconnects that are implemented using optical technologies today. So, this can be the next step forward, that we can also implement some logic circuits, some functions using all optical technologies also. So, some of the advantages here, because light is very fast, you can have high speed computation, power consumption will be low, because everything is depending on the flow of light only, no other circuits are required, and because we are already doing communication. So, electrical to optical and optical to electrical conversions are not required if you can do everything in optical, because you see normally you have a processor, you are doing some calculations, on the other side there can be another processor doing some calculations, and your communication medium can be all optical. So, here you need to convert electronics to optics, and on the other side you need to convert optics to electronics. So, here what it says that if this processing can also be done in the all optical domain, then this conversions will not be required. But the things are not that simple, there are a lot of technological challenges still remaining. Till today, these MZI switches are relatively large in size as compared to the MOS switches which we use in our circuits, and connecting many such switches in parallel is also not so easy, because the intensity of the light tends to fade away or decrease as we connect more number of such switches in cascade one after the other. Okay. And the associated circuitry to drive the switches, see the switches do not consume much power, but the circuits that may be required to drive the switches, they can still consume significant power. So, these are some of the drawbacks. So, once these drawbacks are addressed by researchers, possibly we can have a feasible technology for implementing logic. So, with this we come to the end of this lecture, where we talked about firstly how we can use CMOS transistors to build something called transmission gates and implement multi-way switches or multiplexers using such transmission gates. Then we talked about one of the emerging technologies, the all optical way to implement logic functions. We talked about one such method using Mach-Zehnder interferometer. Now, in the next lecture we shall be talking about another such emerging technology called memristors. Thank you.